Alright guys, we take a little dive into modeling, which is really a section that's in between chapters 2 and our next chapter 3, which actually doesn't come next in Pre-Calc Advanced. We'll end up going to chapter 5, but modeling and optimization. A lot of fun at the end of each chapter in Pre-Calc Advanced. There's a little bit of modeling, and we input it into the curriculum here right after our chapter 2, which is functions, which should make a lot of sense. So we'll get going right away. What does it mean to create a function that models a certain situation? Well, really it means taking real-world information regarding a scenario and creating a mathematical function that defines the relationship of variables in that scenario. Okay. A lot of math terminology there, but very simple. We take real-world information, we create a function or an equation designed to model what's happening. There's really making a connection or a link between variables, that relationship, okay? Maybe it's a relationship between two variables, maybe it's a relationship between more than two, yet somehow we get it down to a function that's written as in terms of two variables. So a lot of the problems that you'll see when we talk about modeling, at least in this section of modeling, we call optimization. Okay, optimization is really when you're asked to maximize or minimize a certain variable. Okay, the maximizing or minimizing of a certain variable. Okay. For instance, this is actually going to come back up in a little bit of a challenge problem, and I want you to think about this as connected to real-world examples and data. But if you can imagine a soda manufacturing company that wants to continue to make cans that have the same amount of fluid inside, the same amount of soda, yet somehow the surface area or the materials that we need to use to make the soda is as small as can be to save cost, for example. Okay, and that's what we're talking about when we talk about minimizing or maximizing. So we'll even write that down. For example, a soda can manufacturer trying to minimize the surface area of a can while keeping the same volume. Okay, so you could just imagine what type of variables would come into play when we deal with that, and we'd want to minimize the surface area. Okay. There's a few different steps. We'll break it down into some steps here, and then we'll give you a quick example here, and you should be able to get a picture of exactly what we're trying to do. So we're going to express the model in words. Okay, very simply, we're going to take that take the information and express in mathematical words. Now this isn't necessarily a step that you have to take. The other option is going to be, I'm even going to give you like picture diagram. Okay, you might see a scenario that you actually want to get a feel for in terms of a visual, a picture, a diagram. Okay, and drawing something like that might also help you wrap your mind about or around what we're trying to do in this problem. Okay, but very simply, for example, maybe we're trying to maximize, again, one of those words here for optimization, maybe we're trying to maximize the area of something. So in words, area equals length times width, base times height. Something, maybe we're maximizing the area of a rectangle. Okay, and the area of a rectangle is length times the width. Maybe writing that down is going to give you an idea of how how to help you get started in that problem. Step 2, we have to choose a variable here, and really we have to choose a variable that we are going to try to write all other variables in terms of the one we select. Okay? You're going to see once we start getting into problems like this, there are going to be multiple variables. In fact, in the example above, it says area equals length times width. That is 3 variables: unknown area, unknown length, unknown width. Okay? We might give you certain pieces of information. We might tell you a relationship between the two. Okay? So for example, if the area equals length times width, okay, and we also know that the width has to be 2 times as big as the length, then really W would equal 2 times L. And therefore, maybe most importantly, we could write area as L times 2L. How did we do that? What was important about that? Well, first of all, we defined some variables. Using the information we were given, we were able to write width in terms of length. And the goal, okay, is to, as we're going to write on the next page, set up the model. Our goal is to have one function written in terms of a single variable, like length in the last one. So what would it be written as? Area equals length times 2 times the length, if we're using last information as a model, or our area would be 2L squared. Okay? That would be an example of a model that we could use to do different things. Use the model. Most of the time, we're going to be using a model by graphing and finding maximum or minimum values. Just like we talked about in Chapter 2, we wonder why we do Chapter 2 first, because we just talked about maximum and minimum values. Or to answer other questions that may be asked. Something like, okay, could we plug this in, call this like y? All right, if you were plugging it into your calculator, really this would be something like y equals 2x squared. Okay, y equals 2x squared would look up like an upwards facing parabola. Let's just go away from that. We're going to skip over that. We're going to go down to the quick example here. A homeowner is looking to fence her backyard. She wants the fencing to go straight back from the corner of the home in the shape of a rectangle. She wants to maximize the amount of space she has for the yard, but can only afford to purchase and install 240 feet of fencing. Find the dimensions of the rectangular yard that would maximize her yard's area. Okay, I took the liberty before, because we try to keep our videos a little bit shorter here, of drawing and labeling. Okay, so we only have to fence 3 sides. Very important here. Okay, and that comes from what was written. We're using the home as kind of the 4th quote-unquote side of this rectangle. Okay, so we want to maximize the amount of space she has for the yard. That would be the yard's area. We know that area equals length times width. Okay, we also know that it says that she can only afford to purchase and install 240 feet of fencing. Okay, that would have to be the perimeter. So 2L plus W has to equal 240. Okay. All right, well, a lot of this stuff will go back to solving systems of equations like you guys used to do back in the day. We had two variables, now we have two equations to work with. Let's solve for one of the variables. W seems easiest to solve for here. We'll subtract 2L from both sides. All right, and now let's substitute that into W. This is step 3 here. Our goal was to have a function written in terms of a single variable, our area written in terms of a single variable. I think we are about to achieve that goal. Our area equals the length times 240 minus 2L. If we want to distribute 240 times the length minus 2L squared, okay. How are we going to maximize this? Well, we're going to plug this into our calculator, okay. Now, if you feel like it, I say, at least as we're working virtually, of course you could use your TI Nspire. Something that might be even easier, because we tend to always have our computer open, is using the Desmos graphing software. So, in Desmos, and I can't switch from document camera to my screen in the middle of a video, so in Desmos we would type in something like y equals 240x minus 2x squared. You would see that it is a downward facing parabola, and when we want to maximize, we want this point right here. Okay. On Desmos, if you were to type in this and find the maximum point, it's really easy. All you do is make sure your screen's wide enough, you click the button, and this point here is 60, 7200. Okay. Now the question asks us, find the dimensions of the rectangular yard. We wrote this function in terms of the length, which means that 60 would be our length, 7200 would be our area. Remember, we want the dimensions, so if the length is 60, 240 minus 120 leaves 120 feet for the width. The dimensions of this rectangular yard that would maximize her area is 60 feet by 120 feet. If we were asked for that area, it is a 7,200 square foot yard. Okay? And that is your first example of an optimization problem. Optimizing, we're usually maximizing or minimizing some variable. Okay, here we wanted to maximize the area of the yard. To do that, we used the information we were given to set up two equations. One basic equation knowing that area is length times width. One extra equation based on the information given. We then used our substitution and algebra 1 skills to write this equation in terms of one variable, area in terms of just the length instead of length and width. And then we plugged it into the calculator, found the maximum point, and used that information to answer the specific questions. So we'll do a lot more of this in class, and some challenging and fun examples. And this is actually, where you guys can start to see mathematics and functions being used in the real world. Okay, I'm sure you guys can think off the top of your head of things that, oh, if you could just maximize this or minimize that in terms of maybe even your future profession or job, that would be a really good thing in that industry, I'm sure.